morning everyone. I'm Dr. Neeti Mittal. I'm MDS in Pediatric and Preventive Dentistry and I did my PhD in maxillofacial surgery, and currently I'm working as Associate Professor in Pediatric and Preventive Dentistry, Santosh Dental College and Hospital, Santosh Team to be University. And today's topic is mechanism of action of systemic fluorides. So, what is fluorine basically? Fluorine is an atom with atomic weight of 9, atomic number of 9 and atomic weight of 19. It has a small ionic diameter, and in the Latin the word fluor means to flow. It's the most electronegative element and it reacts with all elements very actively, and this you all must have read in your basic chemistry classes during 9th and 10th itself. So, if it is ingested during the tooth formation, enamel becomes more and more resistant to caries. If we increase the concentration of fluoride, then changes in composition and structure of enamel, then it may result in enamel fluorosis, but it may also act as an anti-caries agent. That is, it will help in reducing the incidence of caries in teeth. So, and this effect of fluoride is called as karyostatic or anti-caries mechanism, that is stopping the caries or resisting the caries in the tooth structure. And this can be explained by using the following parts in the today's lecture, that is rendering the enamel more resistant to acid dissolution, inhibition of bacterial enzyme systems, and modification in the size and shape of teeth. So, from basic oral histology classes, we know that enamel and dentil, these are two components of tooth. Enamel is the outer covering, which is 85% of apatite, that is the 85% of mineral content, and 12% of water and 3% protein. And dentin has 47% mineral content in form of apatite and 20% water and 33% is protein. So this means enamel has more mineral and dentin has less mineral. So when caries attack happens, enamel takes time to dissolve, while dentin, which is less mineral, it dissolves very faster. Now, just to understand the mechanism of action of fluoride, how it acts, first we need to have basic understanding of the chemical composition of tooth structure. The tooth enamel is formed of apatite, hydroxyapatite, and this is formed of calcium, phosphate and hydroxyl ions. Now, in the basic chemistry classes, all of you must have read that in any solution or in any environment, every product strives to maintain an equilibrium. So, in the enamel, here also is an equilibrium. In the enamel, calcium hydroxyapatite is in bound form, while in the salivary fluids, calcium ions, hydroxyl ions, fluoride ions and phosphate ions, those are all free. So, at a regular pH, there is a balance. There is a balance in the number of ions in the salivary fluid and in the bound form with tooth enamel. But when pH falls, suppose the pH falls from 7 to 5, then hydroxyl ions come into play, and these hydroxyl ions start reacting with phosphate ions and forms hydrophosphoric acid and react with hydroxyl ions and form water. So, as an effect of these, the concentration of calcium, phosphate and hydroxyl ions, it reduces in the saliva. When it reduces in the saliva, it activates the bound form of apatite in the enamel to release free ions in the saliva, and because of this, as an effect of this, the enamel dissolves, and this is what happens during the caries attack. We know that bacteria are producing acids, and that acids cause fall in concentration of ions in salivary fluids, and because of that fall, the enamel dissolves. Now, how fluoride is helping with dissolve, we'll come to know when we'll go through further in this lecture. When fluoride is present, then it is increasing the concentration of available ions. So, when it is increasing the concentration of available ions in salivary fluid, this means that less number of ions will move from bound form of enamel to the salivary fluid. So, as an effect, the less dissolution will happen. So, when the critical pH is 5.5 for enamel, this means this is the pH at which the enamel starts dissolving in oral cavity. But if instead of hydroxyapatite we have fluorapatite, because fluorine is forming tighter bonds with enamel, so the critical pH falls to 4.5 and dissolution rate is very low. So this is the mechanism, like we need to understand how fluoride is reducing the enamel solubility. For this, first we need to understand the crystalline structure of hydroxyapatite. We know that there are calcium ions, phosphatation and hydroxyl ions. Now in this crystal lattice structures, there are two axes A and B which are 120 degree apart, and there is C axis which is perpendicular to this. Like you can see in this diagram, we have horizontal axis A and B which are 120 degree apart, and C axis which is 90 degree apart. Now on the top of this C axis we have hydroxyl ions. Now these hydroxyl ions face each other and cause steric interferences. When these hydroxyl ions cause steric interferences, then these may be shot away from the lattice structure. When these may be shot away from the lattice structure, then voids result in the crystalline structure. Because of these voids, the structure or the hydroxyapatite becomes unstable. Now when fluoride is added to the hydroxyapatite, because of the similarity in size of hydroxyl ions and fluoride ions, the fluoride ions fill these voids. Now fluoride ions form much tighter bond with calcium and phosphate ions because of their higher electronegativity, because of their strong affinity, so the bonds are stronger. So just like the hydroxyl ions used to be shot away because of steric interferences, the fluoride ions are not shot away because of these steric interferences. So the crystal becomes stable. That is how when an acid attack happens, then the solubility rate is really low compared to hydroxyapatite. And so the systemic action of fluoride on caries, or the anti-caries action, is reducing the solubility of enamel, and this is because of stabilization of apatite lattice. Now how fluoride is able to stabilize the apatite lattice? This is because of few of its properties, like the small ionic radii and the ion. There is not much difference in the ionic size of fluoride ions and hydroxyl ions. That is how it is able to replace the hydroxyl ions. It is able to fit almost similarly in that lattice spaces where the hydroxyl ions were, because it is similar in size to the hydroxyl ions. But because fluoride is highly electronegative element, it forms much tighter bonds. So that is how the crystal becomes stable. So what is the calcium formula? I'll say that hydroxyapatite is Ca10 PO4 6 and hydroxyl twice. When we add two fluoride ions, then hydroxyl ions is replaced by fluoride, so it becomes fluorapatite. But do you assume that all the enamel is able to be converted to fluorapatite? No. It is all the enamel will be converted when the concentration is 2000 ppm. So that is not happening in oral cavity, so this is not happening. So only 5 to 6% of hydroxyapatite that is on the superficial surface of the enamel is converted to fluorapatite. So these are the crystal structures of fluorapatite, and this is the hydroxyapatite. You can see that hydroxyl ions are lying here, and these sometimes these will be facing each other and steric interferences will happen, and these are lying a little above the plane, and that causes a little instability in the plane, while the fluoride ions are sitting right in the center, very well placed. There is no steric interference, so there is no replacement. So what are the other mechanism which decrease enamel solubility? First one was that under the influence of fluoride, the solubility of enamel is reduced. We need to remember 2-3 points regarding this, that fluoride ion is replacing hydroxyl ions and hydroxyapatite. In place of hydroxyapatite is being replaced by fluorhydroxyapatite. Why fluorhydroxyapatite? Because it is not that 100% of hydroxyapatite is being converted to fluorapatite. Only some of the percentage of hydroxyapatite is being converted to fluorapatite. So it is called as fluorhydroxyapatite, because both of the agents are present together. Now the pH of solubility of enamel or the hydroxyapatite is 5.5, but because fluoride is forming stronger bonds, So this pH falls to 4.5. So when we are eating the carcinogenous food items, the acid is being formed and the pH is falling down, then hydroxyapatite can dissolve, but fluorapatite still had got some time to save itself. That is how the resistance of against caries is increased. So what is the other effect? What fluoride crystals, what hydroxyapatite or what fluorohydroxyapatite crystals are formed with fluoride? These crystals are bigger with the fewer imperfection. Like in the previous diagram I showed you that the fluoride is sitting right in the center of the triangle and it is sitting perfectly in the lattice, so there are few imperfections, and there is a smaller surface area unit volume for dissolution. This means small area of crystals is exposed to the acids for dissolution. If the small area is exposed to acids for dissolution, less of the crystals are dissolving. And because when fluoride is being incorporated into the crystals, it has tendency to, you know, exclude the impurities as well, like the carbonate ions, magnesium ions. So it is pure fluor hydroxyapatite compared to the previous hydroxyapatite which was present. And another property of fluoride is its enzymatic action, its biologic action. All of us must have read in the basic karyology that when the bacteria are there, they are producing acid. So that acid is dissolving. If we interfere with that acid metabolism of bacteria so that less acid is produced, then what will happen? That there will be less caries because there will be less attack on hydroxyapatite crystals. So this first important property of fluoride, ability to inhibit enzymatic action and so affect a direct effect on plaque bacteria, was first observed in 1940 by Bibi et al. And then in 1954 by Wright and Jenkins. What they did, that they took small amount of fluoride, 1 to 10 ppm, and they showed that it is decreasing the acid production by pure culture or by saliva glucose mixture. So Jenkins again in 1959 showed this, that the higher concentration 32 ppm were stopping this action of plaque bacteria. Sucrose rinses led to, they did a series of experiments and they made people drink sucrose rinse. So when people drank these or rinsed with these sucrose solutions, then as an effect of this their pH should fall. But if there was fluoride in the plaque, then the pH fall and the pH was low. This means bacteria were not able to produce acid. So there was something like, okay, this fluoride is able to interfere with the acidogenic production by bacteria. So this is called as antibacterial action of fluoride. How it happens? It happens by two mechanisms. First is by enzyme inhibition. Second is by, there is a proton pump in the bacteria and this fluoride is inhibiting that proton pump also. So how that is happening? We know that there is a glycolytic pathway in bacteria, and that glycolytic pathway converts glucose to lactic acid, like glucose phosphoglycerate, and enolase is the enzyme responsible which converts phosphoglycerate to phosphoenol pyruvate. Now fluoride acts on this enolase enzymes, it inhibits it so that no lactic acid is produced. This means there is less acidogenesis. Another action is that we know when the acid is being produced in the bacteria, they have that so much of hydrogen ions or the protons are being accumulated in the bacterial cell. So these can be harmful to bacteria, but as a protective mechanism to ward off the bacterial culture or the bacterial internal environment of its cell, the bacteria have a mechanism that is hydrogen proton gradient motive force or proton pump. So they are pumping these all protons from inside to outside, like the extracellular environment. What fluoride is doing, it is acting as a proton carrier and it inhibits this pump, so all the protons stay inside, and it what it causes acidification of bacterial cytoplasm, it inhibits glycolysis, it inhibits those polysaccharide formation, intracellular polysaccharide formation, and it inhibits macromolecular synthesis and export. So this is how it acts as a proton pump inhibitor. And there is also another mechanism that happens as very low, like the sub-millimolar levels of fluoride, that is the enzyme inhibition. I already cleared that it is inhibiting enolase enzyme, so it is inhibiting the glycolysis pathway. But fluoride also inhibits urease, phosphate ATPase, phosphatases, heme catalases, heme peroxidases, fluoride ATPases, nitrogenases, and it also, how it is inhibiting, it may directly bind to the enzymes, or it may bind to some metal fluoride complexes which are responsible for bacterial metabolism. So that is how it acts as anti-crease mechanism, because it is also interfering with the plaque bacteria. Another mechanism of action of fluoride is believed to alter tooth morphology, like reduction in the cusp height, decrease in the fissure depth, and increase in the fissure width. We know that pit and fissure morphology is responsible for caries. The plaque may accumulate there, and this may be, the toothbrushes may not be able to clean in those depth and crevices of pit and fissures. So what fluoride does, it alters the morphology so that pit and fissure become a little more cleanable. Like it reduces the cuspal height, it decreases the fissure depth, and it increases the fissure width. And this is as per observation by Ascendon in 1974. But fluoride may also have an effect during the cell proliferation, cell differentiation, and cell function. How it can interfere with the cell function, like it can interfere with synthesis of protein matrix, secretion of partially mineralized matrix, alteration in matrix composition, mineral deposition during the secretory stage, or mineral uptake during the maturation. A series of experiments have shown that fluoride mostly acts during the mineralization phase of tooth development. We know when the tooth development is happening, the ameloblasts are organizing, and they have various stages, and the last stage is mineralization and maturation stage, which happens after the differentiation of ameloblast has happened. Now these matured ameloblasts, first they will secrete the proteins. When mineralization will happen, the removal of protein will happen by selective protein dissolution enzymes. After removal of these proteins, the mineral will be deposited. Now what fluoride does, it interferes with this mechanism of mineralization. How it affects partially mineralized enamel, and it also affects the newly erupted tooth, where the mineral is developed but it needs to be matured. So on partially mineralized enamel, it has an irreversible effect, and such enamel becomes hypermineralized with disordered crystalline structure, and that is even have 0.5 ppm fluoride administration. So these low concentration of fluoride are also causing irreversible effect on the mineral crystal. When a newly formed tooth is exposed to the fluoride, it may not mineralize fully, because fluoride is interfering with the crystal deposition, and this is a reversible process. When fluoride is removed through the media, the mineralization may happen. So during the early maturation stages, just a recap of what I just stated, that proteins amelogenin and enamelins are hydrolyzed and removed, and this is important for mineralization of enamel. Proteinases help in removal of proteins, and these proteins inhibit the crystal growth. Now fluoride is interfering with these proteinases activity, and it delays the removal of proteins. So when the proteins are there, the mineralization does not happen, so hypomineralization happens. And this was all because of the hypomineralization. This step is called as fluorosis. The tooth has an abnormal appearance compared to a normal tooth, and it appears chalky white, and because there is more and this is irreversible process, and it cannot be treated once the fluoride is removed from the environment. So thank you all, and this was all about the mechanism of action of fluoride, and in the next class we will cover about the types of fluoride used in operatory and by general domain, like the general population. Thank